Good evening, everyone. It is almost 6. Actually, it is 6 o'clock. Let's get started. Uh, so before we start anything new, let us just continue the problem what we were doing last day. Let me share the Jamboard with you. Uh, here is my Jamboard. So this was the problem that we were dealing with last day. It's about this system which has a 32-bit system running on 1.6 gigahertz memory, sorry, 1 gigahertz clock, 1.6 gigahertz clock, and it has connected to the memory, and we basically did the previous problem like size of the memory, and before that calculate the clock period, etc. We did that. So now it is time to basically go to the last part, which is how long will it take to complete this 2.5 million memory access in the millisecond unit. So this is important. Units are important. Please pay attention to them. So units, the milliseconds, and the main like couple of things you need to actually take out from this problem, or at least start highlighting on those part. One is that important part is you need 2 clock cycles for completion of read and write operation. That's important information. And also the processor takes 1 clock cycle. That's another important information. This takes 1 more clock cycle to consume data from the memory. So during this operation with a single instruction, now this processor is generating 2.5 million of a continuous read and write operation request. 40% are read operation, and then 20% of the write operations, they are successor to a read operation request. That means whatever number of write operations are there, 20% of them is an back-to-back read and read to write scenario that we need to, in those scenario, we need to actually consider this 1 extra clock cycle. So now to do that, let's solve that problem. Basically, I believe we did it in a group maybe last day. Please check your answer with these or steps. Maybe let me do that this time. So first we need to make sure we have this clock period. So we have the clock frequency, and from that we need to have the clock period ready. So this is like maybe T equals 1 by frequency, which is given as 1.6 gigahertz, which is basically gigahertz is 10 to the power 9. So it is 1.6 10 to the power 9 hertz. 1 by hertz is second, and 1 by 1.6, if we calculate, it comes about 1.6, 0.625, 0.625 multiplied by 10 to the power minus 9 second. And we all know 10 to the power minus 9 second is a nanosecond. So let's just make it in a nanosecond unit. So this is my time period. And now we start with this type of problem with just no consideration of the special situation. Okay, let's say there is no 1 extra clock cycle to consider. Then in that case, we can calculate the total number of cycle needed as like we have total 2.5 million operation, 10 to the power 6 multiplied by 2, right? That many cycles, like this many cycles to complete 2.5 million operation without extra cycle consideration, right? Without extra cycle. So this is the one that we need to need these many cycles we need to have if we don't consider that extra clock cycle delay due to back-to-back read and write operation. Now let us consider that back-to-back delay operation. Basically, this is how many? Like we have 2.5 million and 60% of them are write operation, right? Because 40% of them are read operation. So 60% of them is write operation, which is 0.6. And out of those number of write operations, we have 20% that back-to-back read to write scenario. So it will be like 0.2 another. So this many cycles extra, right? So we add them up, these two quantities, we add them up. So it is like 2.5, which is basically 2.5 into 2 is a 5, right? Yeah, this is 5. And these quantities 2.5 multiplied by 0.6 multiplied by 0.2, which is 2.5 multiplied by 0.6 multiplied by 0.2, which is 0.3, which is 0.3. So these quantities, this multiplied by this multiplied by this is like 0.3, and 2.5 multiplied by 2 is 5, and all together multiplied by 10 to the power 6, this many cycles, right? This many cycles. So total time is 5.3, this summation multiplied by 10 to the power 6 multiplied by our clock period, 0.625 nanosecond. Now 0.625 multiplied by 2, 5.3 is 3.3125. This is 10 to the power 6 multiplied by 10 to the power minus 9 second, right? Remember this nanosecond is 10 to the power minus 9 second. That's why this minus 9 came. So this is 3.3125 multiplied by 10 to the power minus 3 second, which is nothing but millisecond. That's what our target is, right? 3.3125 millisecond, because our problem asks us to solve this answer in terms of millisecond. So that's the solution of this problem. Question?
I have a question.
Yes, please.
Why is it that for the first one, you multiplied by 2 at the end, but the second one, you didn't multiply by 2?
The second one is basically we are talking about this extra clock cycle, one cycle wait. The first one, the entire 2.5 million operation, the entire 2.5 million operation, and each of them takes 2 clock cycles. That's why 2.5 multiplied by 2, that million cycles to complete that. Now, we are considering in this part, we are considering how many extra clock cycle we need. We need extra 1 clock cycle for each back-to-back read-write operation. And how many are there? There are 60% 60% write operation, and out of 60%, 20% of them are going to have a back-to-back read-write scenario. So that's why it is 2.5 million multiplied by 0.6 multiplied by 0.2 multiplied by 1 clock cycle. So it doesn't matter whether you multiply by 1 or not, but it is not multiplied by 2.
Thank you.
I had another question.
Yes, Charlotte.
How come a back-to-back read-to-read operation doesn't take the extra clock cycle?
Because this way, like while it is processor is consuming the data from the memory, it can still issue the address for the read operation. Maybe let me see if we have a timing diagram somewhere.
So I guess like the address line is available. I mean,
Address line is available, and yeah, address line is available, and it is something like this. So let's look at through the timing diagram. Let's say this is my clock signal. Clock. Let's say this is my read signal. So at this, let's say at this point, we are going to do a read. So my write signal will stay low at this point. And what processor needs to send is an address from where it needs to read. So basically at this point, it will send out the address. Okay, ADDR, some address. And based on that, based on this request at this time point, memory will send the data, corresponding data at this time point, right? And now think that you are going to do another read, okay? So what the processor needs is to send another address during that cycle, DDR1, during that cycle, while it consuming this data incoming from the memory. This data is coming from the memory, right? This is from, let's say, mark it. This is from memory, right? This data. Now, and for that as well, also we can just, it can keep the read signal to high for time being, so that it becomes like a next read signal. Now, for this read, the corresponding data will come at this cycle. So this is also from the memory. Okay. Now you, let's say we want to set up a write operation at this point. So what shall we do? We shall keep the read 0 and write to 1 at this cycle, right? And we means the processor need to send an address, write address. This is a write address. But for the write operation, processor need to sense the data as well. But during that cycle, see the data bus is already loaded with the data from the memory, which is not being processed by the processor yet. Like processor is still in the consumption of that. So processor cannot overload the data bus at the same time when it is consuming the data from the memory. And as a result, it cannot send the what data to be written into the memory. So that's why it is not possible to make an write operation right there at that time point. But what all we need to do is wait for one cycle and then make a write operation. And during that, now processor can issue a write address and processor can issue a data. So this data is from processor, right? Make sense, Charlotte?
Yeah, that makes sense. Thank you.
Okay. All right. So any other question so far on this?
Yeah, just
Yes.
a clarification. So the read cycle includes the time it takes to pick up that data, right?
Yes.
That's what it.
Yes, exactly.
Yeah, that's it. Thank you.
Okay. So I think now we can move to our next topic at this point, if we don't have any other questions or queries. So next topics includes the number system, which is very important. And also, like today's topic was supposed to be programming a computer. You start with that concept, what is a program and everything. So first of all, is there any question on those two topics, like lecture 3 and lecture 4?
I did put one question in the discussion about lecture 4.
Oh, really? Okay, let me just take a quick look. Just
Yeah, it was just before class.
okay. Okay. Okay, so okay, so you have two. Okay. An opcode is 6 bits, a register address is 5 bits, and so forth. This means the hex value for an assembly code instruction is not the same as the hex value in the machine code. Assembly code ADDI has an opcode 08 which become 20 in machine code. Yes, like okay, okay. I'm just trying to understand your question. Like opcode 6 bit, register address 5 bit. Okay. Hex value for an assembly code instruction is not machine code. Assembly code. So what do you mean by hex value for an assembly code of the instruction?
It was from the video where you said that when you had the ADDI mnemonic, then it puts an OP code of 08 in the OP code section on that line.
Okay,
I mean,
okay, let me go to that example of the ADDI.
since it's a I type operation.
Okay. lecture 4 we are talking about, right? Okay, so eight. Yeah, exactly. So it is 8. Yeah. So basically, this opcode is 8, means 08. And remember, like 08 is in a 6-bit representation is this, right? And this is 6-bit, then 5-bit, etc. But when we are trying to change it to the machine code, or sorry, not. So this is the machine code, right? This binary is the machine code. When we are trying to represent that machine code in a hex format, then we are chopping off like four group the 4, and each group of 4 is represented with its corresponding hex symbol, right? And you'll be clear, yeah, you'll probably these things, how that process works of conversion would be, it is from that lecture 3, right? That how we convert from the binary to hex directly. Now your question is how it is basically useful or easy to for handling and determining if my code is an ADDIE or something. Remember, computer does not work on this part. Computer basically works on this part. Okay. For example, if I just can pull my Jamboard. For example, let's say I have and I have a machine code like let me just give an example. I have a machine code like this one. Okay. So how in the world we know this is what instruction is, right? So what shall we do on this process? That's the question. So first of all, Charlotte, machine does not work on the hex code. Hex is for human consumption. Okay, machine is always about these bit patterns or the binaries. So now we have now what machine will do, it knows that my first, like from the MSB side, the first 6 bits, 1, 2, 3, 4, 5, 6, this bit. First 6 bit is my opcode, right? It's always any instruction, I type, R type, J type, they have first 6 bit to look up. And this one is what? This one is somewhat like for human consumption, it is somewhat like in hex 2, 3, right? Hex up 2, 3. So now machine knows that what that operation is. How it knows, let me just pull up one more document for you guys to refer. Bear with me a second. Okay, so this is the MIPS green sheet from the textbook. Okay, and we'll be using it very frequently. I wanted to bring this up for like down the lecture, 2-3 lecture down the line, but anyway, let's pick that up, right? So what this page says about which code is what, right? So look at this 2-3 code, hex 2-3. That means it is a load word. So machine knows this is my load word instruction and which is of I type. Okay. And I type means now I have to make it parse with respect to 5-bit. Next 5-bit is my register. RS, and next 5 bit. So this is my RS or RT. Let me see, just hold on. This is RS, okay. And this one, 5 more bit, is my RT, and rest 16 bits are needed. So practically this one is load word. RS is my register number 3. Okay, so $3, and mnemonic wise it would be a different. So RT comes first. So this one will come first, which is like 2, 4, 5. Register $5. Then RS comes here, register 3 with immediate field 0. So that's my instruction. So now it knows how it basically to deal with that instruction, what to do for that. Is that clear, Charlotte?
I guess I'm not sure why, I guess, how would like a human consume the machine code when it's in hex? Because if you're looking at the code and you know that load word is 2.3, you won't see 2.3 at the beginning of the machine code, even if it's in hex. So I guess like, what's the point of
Okay,
reading
okay. What's the
machine code in
point?
hex?
What's the point? Okay. Remember, these codes are maybe in the easier to write and easier to store in the disk. Like if you are in the text format, if you want to do that, there is no other significance.
Oh, okay. So like you wouldn't look at that and like immediately know what exactly is going on.
No, you won't know exactly what is going on by looking at the hex code. No, you won't. You need to first expand these and then go for that, like parsing process, like breaking up things, look at the opcode field, then determine what are the other fields are.
Okay, yeah, that makes sense.
Okay. Okay, let me see what is the other thing. Okay.
They weren't really related to the lectures. They're just kind of.
Okay, but anyway, it will be useful for the class to know. Let's see. We will MIPS in the exam quiz. Means MIPS means the Mars that simulator we are talking of.
Yeah.
Okay, not really. Like it's not like exams are not like a write a program or something. So you don't need a Mars running Mars for the exam. So yeah, and you have to clear on. I don't mind quizzes. Okay, my first thumb rule. I trust my student. Okay, so if you want to do something funny or goofy, you are cheating yourself. That's my motto. Okay, so it's not none of my concern. So definitely, if you want to learn, like I'm telling all the students, right? So uh, yeah, you can have everything, anything on your desk. You can have your other devices connected to the internet. My only thing is that you do it yourself, the quizzes and exam, and to make sure you understand. And that's why, like quizzes has 2 attempts, right? And they're of same questions, same question sets will come up in the same next attempt too. My whole target is that you will identify which part you are weak and you need more understanding, go back and study those parts once more, make your conception clear, and then come back to the second attempt. So basically you need to do it yourself. Don't talk to any other, like friends or anything. Do it for yourself. That's the only criteria. Other than that, is practically open book, open note quiz, and you can use any resources there. Clear? Everyone? Any question on the quiz attempt?
Yeah, that's very clear.
Okay. All right. So now, since we have good participation, let me go with my poll. of the class preparedness. Let's see how much prepared the class today is. I'm launching the poll for a minute and it's going now. So I need to have 5 more responses complete. 4 more out of 46. 2 more, then we can close this poll. Okay, we have all the polls came in, and let's share the result with the class. About 39%, all of them you have video, watched the video. Yeah, please let's make sure we have the higher number on the all of them part. Reading the lecture note, it's about the same. Some part of is 48%. Please make sure you basically go through them and ask me questions. So basically that's the part. Okay, so as a whole class, you need to improve your preparedness for the today's topics class. Okay. All right. So now let us move on to the next. Okay. Anything on the number system? Everyone is clear about the number system topics? Okay, since there is no question, then let's do some breakout activities now with some number system problem to start with. Let me first assign 47, okay, about 4 maybe. Okay, 11 rooms, 4 to 5 create rooms. Okay. Now the problem is like this. Okay, there is a number system which uses this symbol, do, re, mi, fa, sol, la, ti. Okay, and each of them are equivalent to decimal weight of 0, 1, 2, 3, 4, 5, 6. Like do is 0, re is 1, mi is 2, fa is 3, so is 4, la is 5, and ti is 6. So first problem is that what is the decimal equivalent of the mi, re, do? And then the next one is what is the mu naught? So let's say this called a mu naught number system is the equivalent decimal number of this big one, like 1045673. This is a decimal representation of the value. What would be the corresponding mu naught representation of this value? Okay, so I will give like maybe 10 minutes to solve this, discuss among yourself, solve this problem, and then come up with the answer. So 10 minutes. So any question on this problem? Okay, I'm opening all rooms and 10 minutes starts now.
I'm just writing the question, Professor.
Okay. Okay, time is up, and let's wait for everyone to come back and join our main session. So who wants to explain these two problems? Let's go for the number 1A first. Decimal equivalent. Anyone has answer on that one? No? Yes?
Sure.
Okay, Joshua. Yes?
Yeah. So the problem is the decimal equivalent of mi, re, do. In this case, do is 0. So you multiply. Essentially, you can kind of draw out a little chart with each place. To multiply it against, I don't know, this may be kind of difficult to see, but each place in the number has a different multiplicative factor. So the first factor is 0, so you take 0 times 7 to the
right
0, which is 0, or and then it's 1 times 7 to the 1, which is 7, and then 1 times 7 to the 2, which is 49, and then 2 times 7 to the 3rd, which would be 600. Let's see. That would be 742.
Okay. So this is something like this, right? Mi, re, do, 2, 1, 1, 0. That is coming from do is 0, re is 1, mi is 2. And where did you get the 7?
So since the number system is of base 7.
How do you know this is base 7?
It has I think 7 values. So
exactly. So it uses a 7 symbol. So that's what it is means, like 1, 2, 3, 4. So all these basically musical notes, 7 notes. So 7 symbols are basically there, and that becomes the base of 7. And this is 7 to the power 0. This place is 7 to the power 1. This is 7 to the power 2. This is 7 to the power 3. You multiply between them, right? And then whatever the value addition, you basically add between them. Is that the one you did?
yeah, and then the answer is 742.
742. Others agree onto that answer?
Yeah.
Looks good. So who wants to go for the other one? This one. This is a little bit longer problem, right? So practically what you need to do is basically take that value in decimal, 1045673, and divide by the base number. So you get a quotient, you get a remainder out of this. So note down that quotient. Let's say this is Q1, R1. And then next iteration, you do Q1 by 7, whatever that value is. And that will give you another quotient 2, another remainder 2. And you go on with this process till you reach, you cannot divide by anything, like basically quotient equal to 0. And you have some remainder n. And then you turn this these remainder values to corresponding symbol, right? Maybe I don't know what the value would be, mi, do, re, etc. And then write from the down to up. That's what you need to do to convert this decimal number back to the mu naught system. So anyone has completed that process?
Yes.
So what's your answer? Final answer is there.
Re, re, ti, re, fa, so, re, ti.
Okay, so everyone, you guys need to confirm that whether Matthew did it right or not. Okay, so you go through that process. So anyone else did that answer, came up with that answer?
Yeah, I just did it. I got that too.
Okay, so seems like that's a good answer. So process is a simple, you keep on dividing with the base, determine the quotient, determine the remainder, use that quotient in the next iteration, divide by 7, come up with another quotient till you get a 0 in the quotient, and you have the list of remainder, change it to the corresponding symbol of the number system, and write from down to up, that direction. Okay, at this point, let's take like 4-minute, 5-minute break, 6:55s, we'll be back. Okay, let's get back to Earth. 6:55 over. Let's get started with another problem I have on the Jamboard, which is like this. Represent the value 12 in decimal.
I have a question.
Yes.
Actually, never mind, never mind. I can ask later.
No, that's fine. You can ask now. That's okay. Yeah.
How do you get Ray?
Ray. Okay. I don't know. Okay. Matthew, you want to answer? Ray? On the previous problem, right?
Yeah, I have everything but the first Ray.
First Ray. Matthew, you want to answer? Or whoever did that?
I have the, I don't know, can you kind of read that? It's the remainders. Do you have all the remainders, right? It's probably the last step, you know, the making sure to get to zero, like not remainder zero, but just getting the decimal value to be divided by 7 to be 0, and that gets you the ray in the beginning.
I got it. Thank you.
Oh, yeah, no worries.
Okay, so anyone wants to answer this question?
Sure. I think it would be impossible since the amount, you would need 5 bits in
Thank
2's
you very
complement.
much. Yeah, thank you very much.
Yeah.
Thank you. This is a little bit trick question. So basically, for this type of question with a 2's complement, 4-bit, etc. First of all, you need to specify number of bits, and along with the 2's complement representation, right? These two parts need to be there, because without the 4-bit or number of bit information, 2's complement does not make any sense. You really cannot convert something to 2's complement, right? For example, let's say if I talk about 5 in decimal, and let's say convert it into the 2's complement form, what form that would be? One can say, okay, this is like 101, okay? But see, like if it is a 3-bit 2's complement, then this is a negative value. In a 3-bit 2's complement, what? This cannot be 5, okay? So that's why this number of bit information is necessary. If it is not given in the question, there is no point in solve that problem. And the next one is the range of the system that has been given, like 4-bit 2's complement. What is the range of this number of bits we can represent? Thumbs up rule, that is the range formula is -2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So that is your range for any n-bit 2's complement number system. So for this number system, then your range would become -2 to the power 3 to 2 to the power 3 minus 1, which is -8 to 7. So see this, with this 4-bit 2's complement representation, you are able to represent from -8 to 7. You cannot represent any other value. Definitely the given value 12 is sitting outside that range. So that means you cannot convert that number, express that number in a 4-bit 2's complement representation format. Question? Okay, let's switch gear to this programming, our today's current topic, lecture 4, programming a computer. I'd like to bring attention to 2 interesting facts about the formats. Okay, so this is like let's see, the R type has this format, right? They have the 6-bit of opcode, then followed by the RS, register number, 5-bit, RT register, that specification 5-bit, RD 5-bit, shift amount 5-bit, and function code 6-bit. So total gives 32 bits. These are 32-bit system, MIPS. So we are talking about the MIPS instruction format, MIPS instruction format. So that's the thing. Okay. Now the question is, why 5-bit for the register? Second question is, why 5-bit for the shift amount? Is it arbitrary? Is there something logic? So let's review that. So remember, as a processor, MIPS has 32 registers that you can program. Okay, 32 registers. Now, how many bits we need to actually access 32 register? They are indexed from 0 as a register 0, like as $0, $1, $2 till $31. So they are indexed from 0 to 31. So that means in these register fields, the RS, RT, RD, a value from 0 to 31 will go, right? So 32 different values will be going into this field, RS, RT, RD, etc. So how many bits we need in minimum to do that is log base 2 of 32, take a ceiling of it, there is a 5. So that's why these fields are of 5 bits. Okay. Question so far? All right. Now let's look at this shift amount. What is this? This is a very special field for type of shift instruction. There are shift logical left. We'll review that later. Shift logical right, SLR. Etc. So now see that what this function does. This is kind of instruction like this. SLL dollar, let's say 4 is dollar, let's say 3 by 5. Okay. So what does it mean? This practically mean set the value of the register 4 as you left shift by 5-bit. Left shift by 5 bits. So this 5 goes directly, this bit shift amount goes directly encoded into this shift amount field, in this field. Okay, this shift amount. So though it looks like an immediate instruction, but it's basically an R-type instruction. That's a different story. Now think these registers, all these registers are of 32 bits, right? They are of 32 bits. That means if we do some left shift operation of, let's say 32, then what is the outcome? So all the bits are left shifted, they are thrown out of the register. That means it becomes 0. By the left shift operation, what it does, let's say I have some bit pattern like this. Let's say 1, 1, 0, 1, 1. And let's say I am left shifting by one bit. Okay. The result will become, what will become? This bit will be thrown out. This bit will come here. This will come here. This will come here. This will come here. And a 0 will come here. So my 1 bit shifting for this pattern will result in 1, 0, 1, 1, 0. So imagine you are shifting now, keep on shifting bits in this manner. That means 0 being introduced from the LSB side. And as a result, for a 32-bit register, if we shift all the bit, we basically have 0 as a value. In fact, any value more than 32, 40 bits will be 0. $3 left shift 120 is a 0. So only physical and possible encoded result can be come from a shift range of 0 to 31, right? So that's an valid, that would be a result producing shift operation. Everything else outside this shift range would result to 0. So we don't need to deal with them. We know, like, if the value is this, like more than 31, my result is going to be 0. So that's why we have, now again, 0 to 31, we can encode it with log base 232, that many bits. So that's why we have 5 bit in the shift amount. That means if we are dealing with a 64-bit system, we need 6 bit in the shift amount, because then we need to encode a shift amount between 0 to 63. Question? Okay, now another interesting part. So we know these formats of R type, whereas opcode is 6 bit and function code is 6 bit. And this is R type. Now I type, we have an opcode of 6 bit with some register and immediate field. And we have a J type with a 6 bit opcode. And we have some address values there, doesn't matter. Now question become, this MIPS, how many instruction can it support? Right? So let's look at this problem this way. So we have 6 bit in the opcode field. We have 6 bit in the opcode field. For all these instruction, there are 6 bit opcode. That means we can generate 2 to the power 6 equal to 64 unique opcode. And there is another interesting observation is that your R type, this opcode is always 0, means it's 6 bit 0. So R type instruction, all of the instruction has opcode of 0. They are like opcode, like instruction like add and sub, they are differentiated from each other with a function code. So opcode 0, then we look at the function code. So maybe the add has a opcode 0, 0, and function code maybe 20, and sub maybe have 00. Let's say it has function code of 05. Okay, so that's how they actually, this pair of opcode and function code together distinguish your R type of instruction, and for the R type of instruction function code is always 0. That means there can be 63 max I and J type together, right? Because I and J type does not have any other field to distinguish between the instruction. They solely depend on the opcode, different unique opcodes. So that's why we have 63 max I and J type instruction together. Now, how many R type instruction can be there? So we have these 6 bit of function code. They can distinguish from each other. So another, so 2 to the power 6, 64 R type instructions can be there uniquely. Like we have a unique function code for each of these 64 different R type instructions. So max, I can have 63 plus 64 equal to 127 instruction in MIPS. Though MIPS has way less amount of instruction, it is not 127. It's probably about 50 maybe. We need to. You can go through that MIPS green sheet page and count the number of instructions there. Maybe there are a little more on top of that, but definitely not 127. So all your complex program, like including Facebook, Google, everything, are basically 127 instruction, composed of 127 instruction. For example, if they are implemented on the MIPS. Okay. Question. Okay, if there is no question, then remember next coming Monday is an holiday. We don't have a class. Then we'll meet next Wednesday. Okay, have a good break and make sure you keep working on these lecture videos and all this stuff. Okay, and come back and we'll see you on next Wednesday.